When you have a mixture of two or more components, you will often have to calculate an average molecular weight for the mixture. The most common situation where you might need an average molecular weight if, for example, you have a mixture of A and B coming into a unit, and the mixture is in moles, but the fractions of A and B are mass fractions. Although you can change the mass fractions into mole fractions, it's easier to use the average molecular weight to change the molar flow rate into a mass flow rate. So there are two ways to calculate the average weight of a mixture. One is to use the mole fractions, if that's what you're given. So this would be, for example, Y sub A times the molecular weight of A plus Y sub B times the molecular weight of B. And that's if you're given mole fractions. If you're given mass fractions, then it's 1 over m bar equals the mass fraction of A over the molar mass or molecular weight of A plus x sub B over m sub B. And by the way, you can use this for 2 components, 10 components, however many that you have in your mixture. So let's look at an example here. Let's say our stream is 30% oxygen and the remainder is hydrogen. So first we'll do it using mole fractions. So our average molecular weight is going to be 0.30 times 32 grams per mole plus 0.70 times 2 grams per mole. Therefore, our molecular weight is 11 grams per mole. One thing you should always check is that average molecular weight should be between the two molecular weights that you have. For example, 11 is between 32 and 2. So now let's look at if we do it in mass fractions. So 1 over the average molecular weight is going to equal 0.30 divided by 32 grams per mole plus 0.70 divided by 2 grams per mole. And if you calculate this molecular weight, you find that it's 2.8 grams per mole, considerably different from the mole fraction calculation. So why such a difference? Well, hydrogen has a much lower molecular weight than oxygen. So when it's 70% of the mass, it will dominate the average molecular weight. So let's see what happens when we switch these. So now we're going to have 30% hydrogen and 70% O2. And so if we do it using mole fractions, hopefully you would expect this number to be higher than our first one because now we have 70% of the component that has the higher molar mass. Here, when we do the mass percents, and our average molecular weight is 5.8 grams per mole. Again, considerably smaller than when we calculate it with mole fractions, but it has also gone up because there is more of the higher molecular weight component. So let's use this in a problem. So here we have some unit, and we have 500 grams per hour of a mixture that is 30% O2 and 70% H2, and these are mole fractions. And we want to know what is the molar flow rate. Well, let's take our average molecular weight, which we calculated before as 11 grams per mole. So we have 500 grams per hour, and we divide it by 11 grams per mole. Our molar flow rate is 46 moles per hour. Once we're given this, we can find out how much oxygen there is, because these are mole fractions. So that's going to equal 14 moles of O2 and 32 moles of H2. Calculating an average molecular weight is a simple calculation, but it can make analyzing and solving a material balance a lot easier.